In this lesson, we are going to look at a very famous type of infinite series called a geometric series. You recognize a geometric series as a fixed number r, so r here is a fixed number, being raised to the nth power, where n is increasing as we expand our series. In this particular expression, I've started with n equals 0, but that's not obligatory. The r stands for ratio, because if you look at the ratio of adjacent terms, r divided by 1 is r squared divided by r is r cubed divided by r squared is r, so they have a common ratio. What we are going to talk about today is when this type of series converges and what it converges to. This is a special kind of series in part because we actually know when it converges what the sum is. In contrast to other infinite series, you might be able to look at a series and say, I know that converges, but you can't actually give an exact sum. For a geometric series, we can deduce when it converges and also what the sum is. So let's start with two examples. I want to give you visual arguments for two geometric series which converge, and then we will do the general computation in order to state the rule for when a geometric series converges and what it converges to. Let's start with this specific example of a geometric series where r equals 1/2. I've written this two different ways. The first way, you recognize here that r is 1/2 because we see r raised to the nth power. The second way is perhaps a little bit more common because if you take the numerator 1 and you raise it to the nth power, it's just 1. So we often write this kind of series as 1 over 2 to the n. You have to recognize that that's 1/2 to the n and then identify it as a geometric series. For this particular example, notice I've changed the lower index compared to the previous slide. I'm going to start at n equals 1 just for the geometric illustration that I'm going to give you in a minute, but let me write out what this would look like. So since the first exponent that we're raising r to is 1, the first term in this series expansion would be 1/2, then 1 over 2 squared, so a quarter, then an eighth, then a 16th. I'm going to write out a few. 1 over 32, 1 over 64, and we would continue this forever. It turns out this series does converge, and we can reason geometrically what it would converge to. So I'm going to take each of these terms, a half, a quarter, an eighth, etc., and present each of these quantities as an area. So for our first area, consider a rectangle whose width is a half and whose height is 1. The total area of this rectangle is a half. Now let's attach to that a square whose sides are both 1/2, so that the area of this square is a quarter. Next, let's go back to a rectangle. So this rectangle has width 1/4 and height 1/2, so that its area is an eighth. Now we're going to have a square whose side widths are both a quarter, so that the area of this square is 1/16. And you can see what we're doing. So next we'll have a rectangle, then we'll have a square whose area is 1 over 64. And if we continue in this way, we're filling in this square whose area is 1 unit of area. So that tells us if we kept going with this expansion, we'd be filling in the top right corner for this square. So we know that this series converges, and what it converges to is the number 1. Now let's look at a similar example. Here, r is 1 over 10. You can see the two different ways which you might see this kind of series written. I prefer the second way that looks like 1 over 10 to the n. Notice, just like in the previous example, we're going to start with n equals 1. So if we start to expand this series, because the first exponent for r is 1, our first term is 1 over 10 to the 1, so 1/10. And then 1 over 10 squared, so 100th, and then 1,000th, and we keep going. Instead of writing these numbers horizontally, let me stack them vertically. And instead of writing them as fractions, let me write them as decimals. That works really well for this example because of our base 10 number system. So this first number, 1 over 10, this is the number 0.1. And then 1 over 100 is the number 0.01. And then 1,000 is 0.001. And we keep going in this way so that all of our 1 over 10 powers, if you will, can be written as decimals like this, where it's the next term always picks up another 0. If I try to add up all of these expansions, or rather all of these decimal presentations for these numbers, let's add them up. Notice that each column, if you will, each decimal place has exactly one 1 and the rest are zeros. So we can add up these numbers and it's going to be 1, 1, 1, 1, 1, et cetera, et cetera. It's the number zero point 0.1 repeating. This number exists and it's actually equal to 1 over 9. Let me show you how to figure out that this repeating decimal is the fraction 1 over 9 in case you haven't seen this before or you haven't seen it recently. Let's give this number a name. In fact, I'm going to call it S for sum because it's the sum of an infinite geometric series. So let S be the number 0.1 repeating. I'm going to take S and multiply it by 10 because that will slide the decimal over. So 10S is, if I slide the decimal over, we'll have 1, but then we'll still have repeating ones after that. So 10S will look like 1.1 repeating, which means now that if I take 10S and I subtract off S, the 0.1 repeatings are going to cancel. They have the same decimal part. So 10S minus S is 1.1 repeating minus 0.1 repeating. The repeating part cancels, and we're left with just 1. That means that 9S equals 1. And that's how I got that the sum of this geometric series is 1 over 9. So now that we've seen two examples of geometric series which do converge and we were able to figure out what the sums were, let's look at the general geometric series. So we'll go back to that R notation and we'll figure out what values of R allow convergence and then also what would be the sum. We say that an infinite series converges whenever the sequence of its partial sums converges. So let's write down the first few partial sums for this geometric series, and then we'll figure out what we can say about that sequence. In particular, when does it converge? So the first partial sum is what we get when we add up the series from n equals 0 through n equals 0. Actually, we'll just take the first term. So that's 1. Okay. The second partial sum is the sum of the first two terms. So that's 1 plus r. Then the third partial sum is 1 plus r squared. What we are generating here is an infinite ordered list of numbers. It's a sequence. We want to see if the sequence has a limit. And if it does, then that means that the series has a limit. In order to discuss whether or not a sequence converges, you usually want to have some kind of representative form for the entire sequence. So let's figure out what the nth partial sum would have to look like. Well, it's going to look like some kind of sum. Notice that each of these stopped when the power on the ratio term r was 1 less than the index for the partial sum. So here we went through 1 plus r to the 1, that's 1 less than 2. Then here it was 1 plus r squared, 2 is 1 less than 3. So the nth partial sum should look like 1 plus r squared all the way through r to the n minus 1, 1 less than this index. Okay, this is the nth partial sum, but I claim that there's a much better way to write this. Let me write it down and then I'll prove to you using long division that it's true. This nth partial sum can be written as a ratio that looks like 1 minus r to the n divided by 1 minus r. Notice in this expression that r can't be 1. That's okay, though. We can figure out what it would be if r was 1. Notice if r was 1, then our sequence of partial sums would be 1, 2, 3. So this would have to be n. Okay, take a look at that. You may have seen this kind of expression before, but just in case you haven't, let me use long division to justify that this nth partial sum really can be written this way. So what I'm going to do is long divide this numerator by this denominator. I think it's easier with polynomials to have the powers in descending order. So I'm going to write negative r plus 1, that's the denominator. Let's divide that into the numerator, which I'll write as negative r to the n plus 1. Okay. Now it's possible that n is 1, in which case negative r plus 1 divides into that one time and we're done. But if you're talking about like the nth term in a sequence, you typically want to imagine that you've gone out 50 terms or something like that. So picture n as kind of a large exponent, if you will. What would I multiply negative r by to get to negative r to the n? The negatives are already there, so this would be positive r to the n minus 1. Now to do the long division, let's take that term and multiply it by negative r plus 1. We get negative r to the n plus r to the n minus 1. Subtract. The leading terms cancel, and we're left with r to the n minus 1, negative r to the n minus 1. Whenever I'm doing polynomial long division like this, I like to just bring everything left over down every time. So the plus 1 is just kind of left over. Let me bring it down. And now notice that we have the exact same type of expression we started with, just the n has decreased to n minus 1. Let me do one more round of this, and then we will let ourselves do dot, 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 because there's a clear progression for how this long division is going to go. Okay, to get from negative r to negative r to the n minus 1, I need to multiply negative r by positive r to the n minus 2. Then when I do that, I'm going to have negative r to the n minus 1 plus r to the r to the n minus 2. Subtract. Again, the leading terms cancel, and we're left with, no surprises here, negative r to the n minus 2, and I'm going to keep bringing that 1 down. Once again, the effect of one more round of this has lowered this exponent by 1 again. So if we kept doing this, eventually we would lower this exponent all the way down to negative r to the 1 plus 1. And at that point, we would be nearly done. So imagine that we kept doing this. So I kept up this pattern until I got this exponent all the way down to 1. So it could be something like n 50 minus 49 or something like that if we did enough iterations. So negative r to the 1 plus 1. We would need to multiply negative r by 1 to get to this. And we would have cancellation, no remainder. Now, this is the form of the partial sum that we started with, just the terms are in reverse order, but it's all the same terms. So this justifies that this expression can be written more concisely as this fraction, if you will. And then this is preferable to work with because we don't have the mysterious dot, dot, dot. It's easier to look at this and try to imagine what will happen as n goes to infinity. So that's our next task. If we can understand what this expression does as n gets larger and larger, then we can determine when the sequence of partial sums converges, and that allows us to know when our original geometric series converges. Now that we have this nice expression for our sequence of partial sums, let's figure out when it converges. I'm going to do two specific examples just to describe what happens for two particular values of r, and then we will make two general cases. Okay, so for my first case, consider r equal to 1. If r equals 1, we actually don't use this expression for Sn, but we saw what Sn was. Sn was literally n. So it was the sequence 1, 2, 3, 4, 5, et cetera, et cetera. As n goes to infinity, this goes to infinity. So this diverges. What if r is negative 1? In this case, the sequence of partial sums doesn't go off to infinity. Look at this. It starts with 1. But then the next sum is 1 minus 1, which is 0. But then the third one is going to be 1 minus 1 plus 1, so we're back to 1. And then we subtract off 1 again, so we're at 0, 1, 0. This is a bounded sequence, but it doesn't converge. So the series does not converge. Both of these examples really could be covered in this third case. So my third case is going to be, what if the size of r is greater than or equal to 1? When that happens, then if you look at r to the n, the size of the terms that we're continuing to add to our series, it doesn't go to 0. In the cases that we've already seen, when r is plus or minus 1, the size is always 1, so that doesn't go to 0. And then if the size of r is greater than 1, so r is greater than 1 or less than -1, it actually goes to infinity. But what's important is that the size of the terms that we're adding to our series doesn't go to 0. So the series diverges by the test for divergence. I'll say the series fails the test for divergence. Okay, so that means that the only values for r left to consider are values between -1 and 1. So let me say, if the size of r is less than 1, or in other words, -1 is less than r is less than 1, then the size of r to the n does go to 0. That doesn't tell you that the series converges on its own, it just tells you that it might converge. But look at how r to the n going to 0 affects our expression here for the sequence of partial sums. We can say that the sequence of partial sums goes to, how about 1 minus 0 over 1 minus r? In other words, the limit as n goes to infinity of the sequence of partial sums exists and is the number 1 over 1 minus r. Okay, let me pause here and let you think about this statement, and then I want to write down what the conclusion is, and I'll also give you an alternate presentation for how to write a geometric series that you might encounter. Okay, so let's write down a conclusion. A geometric series converges if and only if r is less than 1. The geoseries converges if and only if the size of r is less than 1. That means if it converges, the size of r had to be less than 1, and if the size of r is less than 1, then the series converges. So these go hand in hand. The way that I've written this series, we're actually starting here with an index of n equals 0. So let me write the formula that way. What we're saying is that if you have the series that starts at 0 and goes off to infinity, r to the n, this series adds up to 1 over 1 minus r, of course, when r is between -1 and 1. What you might encounter or see in other text or something like that is an a here. So sometimes geometric series are presented this way, but both sides are multiplied by a constant. So just call a constant. You might see that the series from n equals 0 to infinity of some number a, where this is just a constant that's multiplying all of the r to the n terms, the sum of this is that constant divided by 1 minus r. That is this equality, just both sides multiplied by a. Both of these formulas for convergent geometric series are starting with a lower index at n equals 0, but actually our examples that we looked at where we had r equal to half and r equal to a tenth, they started with n equals 1. So I just want to take a couple more minutes to adjust this in case your lower index is not 0. Now imagine, like in the two examples that we saw, our starting index is not n equals 0, but let's just call it k. We have our geometric series expansion here, and notice r to the k divides into every term. So what we'll do is factor r to the k in front so that we can, so that we can write this as r to the k times, then after factoring r to the k out of r to the k, our first term is 1, and then r squared. And this looks like the kind of geometric series that we just added up. So this would be r to the k times 1 over 1 minus r, or in other words, it's r to the k divided by 1 minus r. Let's check this if r equals a half and k is 1. This we already saw. If we have n equals 1 to infinity, 1 half to the n, We compared that to pieces of area and figured out that this sum should be 1. Using this formula, it's going to be 1/2 to the n divided by 1 minus 1/2, or in other words, it's a half divided by itself, so that is indeed 1. That agrees with our earlier work. You can check what would happen if you replace 1/2 here with 1/10. You should get 1/9. So let me write down kind of like the most broad expression, if you will. If you have a geometric series of the form a r to the n, where a is a number, r is between -1 and 1, I'll write that in a second, and n starts indexing at something like 0 or 1, or let's just call it k, this series adds up to a r to the k divided by 1 minus r. Okay. I like to think of this as first term divided by 1 minus the ratio. So if you plug in the first term, you get a r to the k, so that's a r to the k. If you start at 0, you just get a. Anyway, it's first term divided by 1 minus the ratio. This is the sum of a convergent geometric series.